on video here. Good, so this is the file that you'll find on Canvas. This is the online lab B, as I said before, magnetic field and electromagnetic induction. And of course you can read through the objective. This is really important here. Here is the link right here to the simulator that we're going to be using. So you can go ahead and click on that link. There is a web version that you can just use in your browser, or there's a Java version which you can download. Now the Java version typically works a little bit better. However, I'm going to be doing this demonstration on the online version. So either really works, it's up to you there. All right, so this week we're working with magnets. Here is a picture of a bar magnet right here. This is a picture taken from the simulation, which we're going to switch over to in just a moment. But you may have heard of electric fields in your theory class, and if not, don't worry about it. Again, it's nothing you can't handle. An electric field and a magnetic field are similar in lots of ways and a little bit different, but they're similar in the fact that they're both fields. And now when we say a field, it really just means that some area in space has the property that if I put an electrically charged particle or a magnetically charged particle in that space, something will happen to it. It's going to experience a force. Okay, so that when we talk about electric and magnetic fields, it really just means, and especially for this class, it really just means it's an area in space that if you put a particle in there that has a charge or a magnetic charge, it will experience some force and it'll be pushed one way or another way, or maybe it'll spin or something of the likes. Okay, so in this lab, let's see, I'm not going to go through the procedures yet. I'm going to walk through those as we go, but kind of an overview here is that there's a procedure section. There's 5 procedures starting from 1, 2. We're going to go through these in just a sec. And then you'll find at the bottom of the procedures section, scrolling, there is analysis and questions. So these are the analysis and the questions that you're going to have to answer after you've completed the lab. In this case, since it's a purely simulated lab, the analysis and questions are only worth 5 points. Usually they're worth a little bit more, but really it's the data sheet that we're interested in for this lab because we are simulating it. So if you continue scrolling down, you'll find your data sheet. So it may seem like it's in a little bit of a strange order, but the procedures that we saw up above correspond to these procedures down here for the data sheet. And basically, as we go through the procedures, you'll need to carry out the procedure on your own and then write down whatever these questions ask you to write down. Now I'm going to go through a little introduction on each procedure, give you some tips and tricks, but it won't be every single step of every single procedure. So you're still going to need to do the procedures on your own and then record your data in your data sheet here. And as you can see, this data sheet is worth 15 points. So make sure that you're really filling it out, really answering all the questions. All right. I think that's everything about how this lab is structured. All right, without further ado, we'll just jump right into the simulation. So I was talking about magnets before, and our first procedure is just about a bar magnet. All right, so I've got the simulation pulled up over here. Now when you first open it, I'm not sure which tab it'll take you to, but make sure you go to the bar magnet tab. Now conveniently, all the procedures are in the correct order for these tabs. So procedure 1 is the first tab, which is bar magnet. Procedure 2 is the second tab, which is pickup coil, and so on and so forth. We're going to use all the tabs in this lab. So when you first load this up, you should see this bar magnet and this little compass here, and then all of our little options on the side. You'll notice if you click and drag, you can move the magnet around. Now it is a little bit laggy. When you use the online version, the Java version is a little bit better, but either way they work pretty well. Hopefully this is showing up okay over the recording, but anyway, so we've got this magnet that we can move around. You can see it's labeled with a north and a south pole, and really what these poles mean is which direction the magnetic field points. So you've probably heard of Earth as having a north and south pole, and maybe you've also heard that the magnetic north and the magnetic south are shifting on Earth. But disregarding that for a second, the north pole is typically where we say the field originates from, and the South Pole is where we say it ends. But you can really view it as either direction. It's just an orientation, especially for this class. All we need to know is that this field has an orientation specified by north and south. Now, how we could use a compass, and if you've ever used a true compass, maybe out on a hike or something like that, this is how it works, is it has this little needle in the center that aligns with magnetic fields. This is a magnetically charged needle, and so it will always align itself with the magnetic field. So you can see, if I put it right in the center here, all these little red and white arrows all over this page are the magnetic field from this magnet. So wherever I put this compass, you'll notice it aligns with the little arrows around it. Now this is actually how we use a compass on Earth, is of course we're very close to the surface of Earth. We're right on the surface of Earth. And so you can always know which direction is north, because when you hold your compass out, it will align to that magnetic field and point you north. Okay, and of course I can move this around anywhere out here in space and we'll see different alignments. All right, so let's take a look at what the first procedure is. First procedure says, and please follow along in your copy of this. We want to first draw the magnetic field lines. Okay, so go ahead and draw in the magnetic field lines. You can draw them either as these little arrows, or you can draw them as connected lines. It's up to you. And then the next thing we want to do is adjust the strength of the bar magnet to 100 and use the field meter to measure the magnetic field at all these different points on here. So I'm not going to do all the different points, but I'll show you how to use the field meter. So here in our little options menu, we're going to want to turn on a couple things. We want to turn on See Inside Magnet. We want to turn on Show Field Meter. And then we're going to set our strength to 100. Now this lab is pretty good at walking you through all the steps that you need to do to complete it. So if you missed something that I said, just go back to the lab, it'll tell you. Now you notice that this little magnetic field device has popped up here. Now this is what we're going to use to measure our magnetic field. And this will tell us the strength of the magnetic field at this little cross in here. We're going to use this throughout the rest of the lab. So you can see if I drag it around, if I drag it far away from the magnet, the strength of the magnetic field goes down. And here, just to note, B is the total strength of the magnetic field, Bx is the X component of the magnetic field, and By is the Y component of the magnetic field. The units for magnetic field are Gauss, named after Gauss, the famous physicist and mathematician. And we use a capital G for Gauss. So make sure you include those units when you write it down in your data sheet. But anyway, as you can see, the magnetic field gets much weaker as I move it away from the magnet, and gets much, much stronger as I move it over towards the magnet and then inside the magnet. You can see it's much, much bigger here. So there are a few different points listed in the lab manual. You'll want to take a measurement using your field meter here of the magnetic field strength at that point, and you're going to write it down in your data sheet. Make sure you hit each one of these points just to see, and then you'll put those down in your data sheet. Just to show you what that looks like, I'm not going to be scrolling to the data sheet each time, but since we're just getting started here, our data sheet looks like this, and you want to record at each of those different points, record the strength of the magnetic field. Okay. Next procedure. Now we're working with the pickup coil. So we just saw a bar magnet here. Again, we're gonna have the bar magnet again over here. We're gonna notice something interesting. We've got this little coil, we call them a coil of these two, this is just a conducting wire. These little dots in here are the electrons, and you can show them or not show them. They're really proportional to the electrons, and they're not super insightful. But sometimes it's helpful to envision the current flowing through the wires. You can see we've got a light bulb attached up here. Now, the light bulb is not a very accurate way to measure voltage, so we're going to switch over to our voltmeter for our indicator on top of our loop right here. Now, you'll notice that the voltage going through here is 0 right now, and that makes sense. We've just got a static magnetic field out here in space. This is something that we know about physics, and maybe you don't know that yet, but this is the time when we're learning it. So when we just have a static magnetic field sitting out here in space, it has no impact on the electrons in this coil. However, if I start moving my magnetic field so that it changes in time, maybe that's just by me dragging this magnet back and forth, you can see we're starting to get a voltage in this loop. And you can see those electrons moving back and forth. Now this is actually what we call induction. So induction is a really cool phenomena in physics, and actually comes up a lot in the real world. It's used in a lot of our devices. But basically how it works is it says a changing magnetic field can generate a current in a closed loop. Okay, and that's about the depth that we're going to take it for this class. But a changing magnetic field, that is a magnetic field that's changing in time, the strength of it is changing in time, can generate current in a closed loop. So that's exactly what I'm doing here. I'm taking this magnet, moving it back and forth. My magnetic field now around the loop is changing in time, and it's causing those electrons to flow back and forth, and it's actually showing us a voltage. You notice the voltage bounces around, it's not very consistent, but we are getting voltage nonetheless. Okay, so now procedure 2 basically is asking you to try out different ways to induce a current in that loop, in the pickup coil is what we call it, because it's picking up the current. So I just showed you moving the bar magnet, try it at different speeds. A couple other things you can do is move the pickup coil instead, change the strength of the bar magnet, or flip the polarity. So just to show you those really briefly, you can move the pickup coil instead of the magnet. Oops, there we go. You can move the pickup coil back and forth instead of moving the magnet. And now it's a little hard to see, it's a little bit jumpy, but this is why you'll have to carry this out on your own. Now notice that moving the pickup coil is changing the magnetic field inside the coil in time. So the magnetic field in space out here isn't changing, but the magnetic field in the coil is changing because I'm moving it around. And that's what's causing our induced current here. Let's see, then the other things we could try was changing the strength or flipping the polarity. So notice that I flipped the polarity, and for just a moment, this needle bounced around, but then it kind of came back to zero. So if I continuously flip the polarity back and forth, you see that the needle actually fluctuates back and forth. Okay, so you'll get to play around with those some more. So that's our procedure 2. The last piece of procedure 2 is adjusting the number of loops and repeating the above procedures, and then of course recording it all in your data sheet. So that one I'm going to leave to you. Remember, any options that the lab asks you to change will be over here in the right-hand menu. Okay, let's move on to procedure 3 here. Okay, so procedure 3 is about what we call an electromagnet. So in procedure 2, we just learned that if we move a permanent magnet back and forth, we can induce a current in a closed loop of wire. Well, the natural question is, could that work in reverse? Could you generate current in a wire and have that cause a magnetic field instead of a magnetic field causing a current in a wire? And the answer is yes, it does work both directions. So here, basically what I have is a battery hooked up to a couple coils of wire. And I'm just running current through this wire around these coils. And what's happened is we've generated a magnetic field in space. Now what's interesting here, and can be kind of counterintuitive, especially about magnetism, is that here we have our moving current and we're just generating a stationary magnetic field. So notice that these magnetic field arrows out here aren't changing in time, even though we have a current flowing through the loop. Now this is because our current is flowing at a steady rate, and now that our current is flowing at a steady rate, this magnetic field is steady. So what happens if our current wasn't flowing at a steady rate? Well, we can use AC current to check that out. So AC current we only briefly mentioned in class once, and it's all right if you don't know what it is. AC current is basically where instead of your current flowing in the same direction through your coil the whole time, it instead flows one direction for a moment and then back the opposite direction for the next moment, and then back the next direction, the first direction in the next moment. So it's alternating back and forth, and that's what AC stands for, is alternating current. So this little graph here shows us what our current is doing, and you can see if I adjust the slider on the left, I can make the amplitude of the graph bigger, which means that the current is more or less larger. We'll go with that. The current is larger. Or I can adjust the spacing of the peaks like this. I can make the current go alternate quicker, or I can make it alternate slower. So we call this the frequency. Okay, so we don't need to know a whole lot about AC for this, but we can play with these sliders and see what effect it has on our magnetic field out here. So now you notice this magnetic field is sort of pulsing in and out. Okay, it's going, now our magnetic field is actually changing in time. It might be tough to see over the recording, but of course you can always play with it in your own simulation. We can really tell that our magnetic field is changing because our compass here keeps oscillating back and forth. Notice it keeps going back and forth. And you can even see the current here going one direction and then going the other direction. Okay, so something that's unique about electromagnets is that they only behave as a magnet when it's powered, right? There's only, this coil only behaves as a magnet when it's got current flowing through it. Whether that's a static magnet or a changing magnet, it only works as a magnet when there's current flowing through it. So this, actually, we use electromagnets as ways to sort of have portable magnets where we can turn them off when we don't want them and we can turn them on when we do want them. Okay, so for number 3, basically what you're going to be doing here is we're going to bust out our field meter again. And if you don't remember, to show the field meter, just select the show field meter option. And we're going to throw it right in the middle of our loops here. And all you're going to do is you're going to change the voltage. Oh, sorry, I should be on the DC current source first. So for the very first part of this procedure, we just want to be on the battery here. And all we're going to do is change the voltage from 0 to 10 in steps of 2. So 0, 2, 4, 6, 8, 10. And we're going to measure the magnitude of the magnetic field at each step. So all we're doing there is I have my battery. I can drag this slider down to 0, and you see the magnetic field disappears because there's no current flowing through here. And then I'm going to bump it up to first to 2. And you can see that our magnetic field is 60. I'm going to bump it up to 4. Oops. Now we're 120. I'm going to bump it up to 6. Now you can see we're at 180, and so on and so forth. So make sure you record all the way up to 10, and you can see that the magnetic field strength is in fact changing. Then make sure you write those down in your data sheet. And we got a couple more things to play with here. Then we're going to fix our voltage to 10 volts. And we're just going to change the number of loops in our electromagnet. We're going to see how that affects our magnetic field. So I've got my voltage set to 10. Now I'm going to go ahead and just turn my number of loops down to 3. And you can see as I turn it down to 2, to 1, the strength of my magnetic field is actually changing. So we discovered something here, that the number of loops really does impact the strength of the magnetic field in an electromagnet. So make sure that you're recording all of those down in your data sheet. There's a table for that already. Now the last thing, or the last 2 things, I guess, is change the polarity of the battery. Now remember, polarity is just the direction the battery is facing. So if I drag this all the way over here, you can see I've changed the polarity of the battery. The positive terminal is on this side now, and the current is flowing in the opposite direction. So change the polarity and see how that affects your results. And then of course, switch from DC to AC, and then they just want you to record what you've noticed there. And down in the data sheet, there are little questions that kind of prompt you to fill in they prompt you to fill in the data that you've observed. Okay, now we're about a little past halfway done. So now we're moving on to number 4. So number 4 is about transformers. So transformers, you've probably heard the word transformers. They're those little cylindrical boxes that are up on telephone poles. Those are big transformers. And what transformers do is allow you to change the voltage of a certain electrical signal. So we use the transformers on our telephone poles to change the voltage from the high voltage that's supplied by the power company to a voltage that's much more suitable for coming into our houses. Of course, this is not the only spot we use transformers. We use them all over the place. Generally, if you've got a laptop or some device that has one of those big power packs that plugs into the wall, usually that's got a transformer in it. And what it's doing is transforming the voltage of the incoming electrical energy into a voltage that that device can handle or that it really likes to work on. So how does a transformer work? Well, it's kind of like using both things that we just learned. So we're going to have a current supply that is working as an electromagnet. It's going to be generating a changing magnetic field. Then we're going to have a pickup coil. And so this here in this image, I'll just go off of that. This image here is our supply. This is our current source. This is going to be our electromagnet. It's causing the changing magnetic field. And over here, this is our pickup coil. And so the changing magnetic field generated by this electromagnet is going to create a current flowing through this pickup coil. And of course, that will give us a voltage output on our device here. Now, this is the idea of how transformers work. The physical implementation of a transformer that you might see in a telephone box is usually pretty different because people have developed lots of different ways to actually create these things. But this is really the fundamental principles behind this. So, okay, so let's back up. For step number 4, what exactly do we need to do? We need to choose an AC current source, place the 2 coils in the figure below, just next to each other. And then let's see what we're going to do next is set our voltmeter to display, and then we're going to change the number of loops, 1, 2 to 3, and watch as the change, see what happens in the pickup coil. So let's do that part first. So let me switch back to my simulation. I'm going to go to my transformer page here. All I'm going to do is get this set up. So I like to just center these here. I'm going to leave them as they are for now. Going to change this to AC. Then I'm going to take my pickup coil. I'm going to change it to voltmeter here. And let's see, what was the first thing it asked us to do over here? We want to change the number of coils and watch what happens. Okay, so right now we're not getting too much, so I'm going to bump up my loop area to 100% so we can capture more. Okay, good. Going to turn up my coils to 3. Good, there we go. So now you can see the voltage needle is just barely moving. So what I'm going to do here is I'm going to bump up my AC current source, the amplitude. Let's see. And I'm going to bump up the frequency here too, just to really make this drastic. All right, good. So now we can see our voltage wire oscillating back and forth here. That means that we're getting a current in this wire, in this loop right here in our pickup coil. So we can see that our electromagnet is creating a changing magnetic field in space, and then our pickup coil is picking up that magnetic field, that changing magnetic field. It's being converted into current flowing through this, this coil right here, and that's giving us an output voltage. Now notice here, what's really cool about this is that this coil, our pickup coil, is not actually touching our power supply. All right, we're not hooked up with any wires or anything, we just have empty space in between them. This is actually how wireless chargers for phones work. So if you've ever seen a wireless charger, all you have to do is set your phone right on top of the little pad, and it'll actually charge it up. And this is exactly how it's doing it. Inside the pad, there's an electromagnet that is pretty strong, probably stronger than this one because we're not getting much voltage out here. But basically that electromagnet creates a changing magnetic field in the space just above the charger. Well, really in all space, but it dissipates pretty quickly. So the space just above the charger. And then the phone has a pickup coil, just like this. probably has a lot more loops in it because that'll get you a little bit more power out of it. But the phone has that pickup coil inside of it. And when you get the pickup coil aligned with the electromagnet, the changing magnetic field caused by the electromagnet will actually cause current to flow in the pickup coil and allow you to charge your phone's battery without actually plugging it into anything. So it's a really cool phenomena that occurs, and it's pretty impressive that we can actually transfer energy like this without actually having our power supply touch our pickup coil. Okay, so that was a little bit of a tangent there, but it's good to know about these things. So getting back to the lab, basically what you're doing for this one is you're just going to change the number of coils, right? And you want to see how that affects the voltage in the pickup coil. And then you want to play around with the frequency of the current supply and see how the frequency of the current supply and the frequency of the voltage are related. Okay, let's see. Now, the last thing they want you to try is switch to the DC current source and see what if there's any voltage induced in the pickup coil. So if you've been tracking what's been going on so far, you might have a hunch about this already. And in fact, if I change my current source to my DC current source, now my magnetic field in all space is static. It's not changing, which means we're not generating any current in our loop, which means we cannot have any voltage here. So again, I want you to go through this on your own, but that really is the answer right there to this question. There is no voltage induced when you have a DC current source. Okay, now the very last procedure is about a generator. Okay, and now this is an example of how hydroelectric generation works. So maybe you've wondered how hydroelectric power plants work and how we could really convert energy from flowing water into electrical energy. And this simulation is actually a really neat one that shows how a generator works. So if I come over here, they've already got most of it set up for us. I'm going to just go ahead and turn on this faucet by sliding this. As you can see now, this faucet is spinning this wheel that has this bar magnet attached to it. And now the bar magnet is, let me turn on the show field option over here so we can see our magnetic field. Now you can see the magnetic field is actually changing in time, just as we've seen in the previous ones, which is allowing our pickup coil here to have current generated in it, and which is powering our light bulb. Since we've been using voltmeter this whole time, I'll switch to the voltmeter. You can see that this spinning bar magnet, creating a changing magnetic field, is creating a current in our pickup coil, which is giving us a voltage. So now we've essentially converted the energy in this water, and it's really potential energy, right? Because we're dropping this water from a high height to a low height, and it's impacting on the paddles of this wheel and causing that paddle to spin. So we're really converting gravitational potential energy into electrical energy over here. And we could use this to, say, charge something up. We could charge a generator with it. We could supply power to a city with it if we had a very big hydroelectric generation facility, etc. Okay, so all it asks you to do about this is to find out how you can control the frequency and the magnitude of the generated AC signal. Okay, so just to give you a little hint on that, the frequency is controlled over here. This is by the RPMs, the rotations per minute of this bar magnet. So if I turn up my water supply, so I'm supplying more water, the bar magnet's going to spin faster, and so the frequency of our current coming out here will be going a lot bigger. Now, if I just want to change the amplitude, what I can do is just adjust the number of loops. So if I turn the number of loops down, and let me turn the frequency down just a little bit to see, it's a little bit slower. You can see that with only one loop, our voltage is kind of oscillating between, it's oscillating relatively small. But if I turn up the number of loops, say to 3, you can see our voltage is much larger, oscillating back and forth. Okay, so essentially that's what you want to do for number 5, and then you'll of course write down your answers on the data sheet. Now the last thing I'll point out here is just in the analysis questions, make sure that you're really reading them in depth. You should be able to answer each one of them based off of what we've done in the labs here. And of course, even if you don't know the theory, even if you haven't come across magnetic fields or induction yet in your theory class, it's okay. You can totally get through this lab just by experimenting and playing around with these simulations. And that's really what they're for. All right, now the last thing I'll point out here is just number 5, list at least 5 hydroelectric power stations in the United States. This is just to get you sort of thinking about energy and how it works in our country and in the world as a whole. So you'll probably have to Google these, but there are plenty of hydroelectric power stations, and I'm looking for a quick list of 5. Okay, let's see. All right, so that is everything I have for you for this lab. I know doing these online labs and especially simulation labs is a little bit of a strange way to do a lab class, but I think these are really good simulations, and there's a lot that you can learn about magnetic fields and electromagnetic induction through this lab especially. So I wish you good luck on this lab. Of course, I'm always available via email if you need anything. And with that, I'll see you the next time I see you in class.